I was told I should tell a joke to wake everybody up. And I don't know very many jokes, but I do know one joke. And that is, there are three kinds of people in this world. There are those who can do math, and there are those who can't. With that introduction, we're going to, the topic of the afternoon session here is, of course, cloud computing. What have we learned and where are we going in cloud computing for big Earth observation data? Our first speaker is Wolfgang Wagner from the University of Technology here in Vienna. He is a professor of remote sensing, head of the Department of Geodesy and Geoinformation at TU Vienna. His research is in active microwave remote sensing, and that has led to several free and open soil moisture data services operating within the framework of the Copernicus program and EUMETSAT. He is co-founder of the Earth Observation Data Center, a public-private partnership to establish collaborative cloud-based Earth observation platforms and services. So he is going to be up first, and go ahead.
Thank you for the introduction. Also, thank you for the opportunity to introduce here to you the Earth Observation Data Center, which was already, as announced, is a bottom-up initiative to build a federated infrastructure for processing, in particular, Sentinel data. So not so long ago, the situation as a scientist and user of Earth observation data was that you had your own computer and you downloaded data, for example, from the ESA data archive, and you did the processing with your computers at home. So this could be one of the service running at TU Wien, and we were able to download complete data sets from full satellite missions. We could apply our own algorithms, so typically we code our own algorithms. In the past we did it with IDL, now you do it with Python and R. You could make sovereign decisions about what you want to do, so you had no limitations of how you treated the data. And also, very importantly, we could afford it. So we could download complete satellite data and work on a global scale with them. And one of the things, for example, we did is we processed, for example, from the NBSAT Advanced Synthetic Aperture Radar, we processed over 100,000 images to create a global mosaic, which, by the way, is the mosaic that you see in all the Sentinel-1 animations. So if your Sentinel-1 flies over the Earth, this is the backscatter model which is behind it. At that time, it was a great effort, but obviously, when we started to look at that time, it was around 2010, 2011, we looked how at Sentinel-1, we realized that this is not the way how we can continue doing it. Obviously, we realized that the data volume is increasing quite a lot, so we can say that we have roughly a doubling every 2 years, but this per se is not the big issue, because some of the technologies are growing along with the data volume. So Moore's law is still valid. If we look at the prices for disk and CPU, they're not growing as rapidly, but you can still kind of keep on doing. The biggest bottleneck that we are seeing is in the bandwidth. So bandwidth is only growing by about 25% capability per year. So accumulated over all the many years, we see that we have a big gap between our capability for generating and processing data and the way how we transmit the data. And I think this is the fundamental reason why we already see a very different landscape nowadays. So we now see that we have massive data sets being hosted and distributed by ESA, but we now see the emergence of a couple of big data centers and clouds. And again, we as a user, we're somewhere in between. And now we look all around, and the question is, where do we go? And the question is, whom do we trust? So that in 10 years or 20 years from now, we're still happy with our decisions being made. And this is not easy, because data is this is our value, or this is what we live from, and you don't give them easily away. So what is the landscape? We have heard a lot about commercial services like the Google Earth Engine or the Amazon Web Services. Obviously, they have scaled up a lot and provide lots of capabilities. We've also heard about top-down public programs, like, for example, there has been national programs like the German program called Code.de, also the ESA-managed diocese funded by the Copernicus programs, I would say, are a top-down public program. And there is also bottom-up cooperatives, where a couple of people come together saying, well, we want to use our existing capabilities, federate them, and be able to process the data with our expertise. So I would say, for example, the French initiative TEIA falls under that umbrella. There was really a group of public organizations in France coming together to create the TEIA system, of course supported by CNES. I also would see the GEO DIAS as this kind of role model where EUMETSAT and ESAMWF came together with Mercator Ocean saying, let's use our capabilities and extend them and combine them. And I'm now presenting you the Earth Observation Data Center, the EUDC. So the EUDC was founded here in Austria as a company, but essentially it's a public-private partnership. And our idea is to offer cloud computing, supercomputing, and petabyte storage. And the overall idea is that we say, well, we want to create a federated multi-owner IT infrastructure that can be used by scientists, by the public services, and by innovators. And the very important distinction between, say, a typical cloud provider is that we regard that our users are our partners. So they're not just merely buying in, but they can also influence decision-making, so where the center is developing and what are the priorities. And we want to go from the data to model predictions. So Earth observation capabilities are as important for us as modeling capabilities, for example, hydrology or meteorology, to actually start assimilating the data and making useful predictions. It was founded in Austria, but from the very beginning, we always knew that Austria is a small place, a beautiful place, but small. So we already knew that this cannot fly without being international. So from the very beginning, we included partners and from other European countries and even abroad. So now we have a network from partners from the Netherlands, Belgium, Switzerland, Czech Republic, Finland, even Australia, and other countries, Italy. And we also we have a very strong science base, but we also have the companies, and we go up to the users, like, for example, the Austrian Ministry for Environment is already a partner, and, for example, the World Food Programme using the capabilities. So you see, it's quite a diverse network, and this mix of companies makes up the value of it. And what we also said, being used to work with Earth observation data and being used of making these things operational, we said that for all the different functions that you need in an Earth observation chain, you need to have the appropriate equipment. And here, this is basically a role model as being used by the weather forecasting centers, that you, on the one hand, have a near real-time operational capability, but of course, for reanalysis purposes and for the model calibration, you need to have a global testing and reprocessing facility. So you need to have high-performance computing capabilities, supercomputers. But supercomputers are not always handy for doing the work. You also need a cloud platform for the scientists to start doing the work. For doing the testing. So the overall flow of the algorithms, how we introduce algorithms, you first do the development work on a cloud platform, straight and simple. Then you do a testing on the supercomputer, and finally go to the near real-time processing capability. And the infrastructure, we're already trying to integrate across different countries, but say here you see the infrastructure that we have here in Vienna. As I said, the idea was not that we create something from totally on bare grounds, but we started from an existing high-performance computing infrastructure, the Vienna Scientific Cluster, and we bought the storage systems and attached it, high performance, to the supercomputing, and we also started developing the cloud platform. In terms of the storage, we still use tapes because this is a very efficient way of actually storing data, and you don't need to have everything online all the time. And you see, we basically have an appropriate model, a contractual framework that allows us to have a co-ownership of the hardware infrastructure, which is, of course, very important. So I spend lots of time actually talking with lawyers that this can work. So this is very fundamental for the EODC, that this works, that you have a proper setup. And what we have managed so far is, we have up-to-date worldwide Sentinel data from Sentinel-1, Sentinel-2, and Sentinel-3. Our daily data volume is about, the data repository we already have is about 5 petabytes. So this was also a number that Gregor mentioned today that is hosted by the Amazon. And the daily data volume that we get in is at the moment about 5 to 6 terabyte of data. But for us, this is just, the starting point. We want to use ready-to-use data. In the past, we said time series. As a scientist, I always worked with time series. Now I just say, I call it now data cube because that's more fashionable. It's like this. Okay, now we do data cubes rather than time series. We created a global Sentinel-1 data cube already at 10 meters. So everybody who wants to have access to the data can come to us. So rather than the colleagues who said yesterday that this doesn't exist yet, it exists already. And we go further to create image mosaics, water bodies, soil moisture products, wetlands, land cover. So this is our own kind of interest in doing these things. Yeah, and one of the things we have been doing or just completing right now is a project for ESA, where we used all the Sentinel-1 data acquired in 2016 and 17. You see here the number of images acquired by Sentinel-1A and B in those years. You see that Europe has been covered very nicely, some other continental areas as well, some others are not that well. But overall, it's a big data set, and we had about 400 terabyte of data where we started the processing. Along the way, we created something like 1.5 petabyte of intermediate data products. So it's quite a big data volume, and we need a supercomputer, and of course it was running for some weeks to create these things. And what we created was, amongst others, we created non-normalized backscatter images, but we also tried to, as you see here on the right, an image of the backscatter image that tries to take away the incidence angle dependency of backscatter in order to have not so much problems with striping effects in the data if you don't do this properly. And the other thing we are doing is we creating a Sentinel-1 operational soil moisture service for the Copernicus Global Land Service. For example, this soil moisture product, the algorithms are so complex and we need to calibrate our algorithms. We would not be able to do this on Amazon. We would not be able to do this on the Google Earth Engine. We need our own infrastructure. So I think that this is often forgotten, that once you have very complex algorithms, it doesn't just work with these cloud infrastructures where you basically have an image in, image out architecture. You need to have more complex things. Yeah, when you see this animation, you basically see when it's brown, it means dry soil. When it's blue, it's wet soil. And in this kind of Sentinel data, we see for the first time very nicely all the weather fronts and rainfall affecting the soil. Very nice. So what's our experience with the EODC, and my take-home messages from some of the past work that we have been doing? So it's not just the big IT companies who can do the job. It's not just Amazon and Google we need to go to, but federation works. We can do it. And the advantage of federation is if you bring together those people having experience in the data, this is the starting point because the value is in the data in many cases. Of course, the IT needs to go along with it, but the IT is just one aspect. You need to have expertise on the data, and you need to have expertise on the algorithms, and you need to bring everything together. And when I look at the users of the EODC, like, for example, the Austrian Ministry for Environment, they appreciate that they have somebody to talk about the quality of the data products. So they appreciate the scientific advice. So rather than going somewhere where they don't know how the things are being made, they trust, at least they have the personal context still. And also the last comment, this also reflects a bit my role as the current chair of the Terrestrial Observation Panel for Climate. Be aware that many things in Earth observation we cannot commercialize. It's impossible. Try to sell a commercial product on shrinking glaciers. This is expected to provide a publicity. And many of the models that we have right now that want to build up these clouds are based on the view that everything can be commercialized. This is not possible. So I think these commercial business models of those clouds need to be revisited. And that's why also I think the public hand in these things is so important. Particularly if you think about climate change, land degradation, you really want to make sure that this is not being serving just commercial interests. So in terms of the outlook, obviously it's very impressive what's going on, and sometimes it's also very hard to actually move in that environment and think about how you can, survive in a very competitive environment. But I'm also very hopefully looking into the future, because what I'm seeing is that open science is changing the way how we do things. And that sometimes these kind of open science movements are acting much faster than you would expect them. So, for example, the fair data principles are now, for example, in Austria being implemented by the Austrian Science Foundation. So now if you put in a scientific proposal, you need to say how you cover fair data principles. European Open Science Cloud, also not something very simple, a very complicated process. You need to bring people together, but it's growing. As I see the GEO is also a very nice one. And just to say that, for example, the GEO and with the UDC, we are federated. So if you go to the GEO DIAS, and if you want to connect, if you then want to get Sentinel-1 and Sentinel-2 data, you get to the EUDC. So that's also, in that sense, I appreciate very much these efforts to federate. And last but not least, I'm also looking forward to Ed's presentation in OpenEO, which is our joint project, where we already see that the community is picking up, and where the idea is that you start to create interfaces to different clouds so that you don't have this login that is currently so problematic. With this, I thank you very much for your attention. Thank you.
Okay, thank you very much, Wolfgang. Let's move on next to a presentation by Julia Wagemann from ECMWF. We heard from Julia yesterday, right? And she is a PhD candidate at the University of Marburg and a visiting scientist at the European Center for Medium-Range Weather Forecasts. She works on the interface of open climate and meteorological data, user requirements, big data technologies, and cloud computing. Her main interest is in how cloud computing and big data technologies can be leveraged in order to offer user-friendly, scalable data services. And today she shares the current status of the Copernicus Climate Data Store, and will present preliminary results of a user requirement survey she conducted together with ECMWF Data Services. So she's got actually two presentations, and we'll go a little bit longer than the others. Okay.
Okay, thank you. Yes. I start. So my presentation is a combination of two projects we have at ECMWF, and also to show in a direction we interested in, but we also try to still figure out what users actually want, and how data organizations like ECMWF also could transit to cloud services. And I just came across this cartoon some weeks ago, and everyone talks about cloud computing and cloud services, and this is the next way. But it's a lot of work in order to make cloud services happening, and also that users can actually leverage it. And my first part will be to present the current status of the Copernicus Climate Data Store. It's now moving more from Earth observation data to climate and meteorological data. And the second part is then to present preliminary results on a user requirement survey we conducted. I think I need a... So yeah, like just a quick overview about ECMWF and Copernicus. ECMWF is the European Center for Medium Range Weather Forecasts. We are a 24/7 operational center, and we produce global numerical weather predictions. We have one of the largest meteorological data archives worldwide, which we have more than 250 petabytes available. And at the same time, we operate two Copernicus services, the Copernicus Climate Change Service and the Copernicus Atmosphere Monitoring Service. And thus, due to Copernicus, also we have a wealth of open environmental data available on climate, air quality, floods, and fire. And yeah, they are ready to use and to be used. But how it was, as an example here, or it's a bit broken, it's one of the most popular data sets is the ERA 5 data sets. And just to have a quick overview, it's in total, the entire ERA 5 data is around 5 petabytes. It's more than 100 parameters on atmosphere, land, ocean, climate variables. The spatial resolution is compared to Earth observation data still not as good, but we are getting better. From ERA interim to now ERA 5, it's now 30 kilometers spatial resolution, but the hourly now we have our hourly temporal resolution, which is very good and valuable for many applications. And now we have 41 years of data available from 1979 to almost real time, so about within 3 months of real time. But it is planned by the end of 2019 that the data set is actually extended back to 1950. So we have a lot of data available. But yeah, as we also heard yesterday from many, it's just the beginning, to make the data openly available. We also have to find ways to make the data better accessible to users. And the Climate Data Store from Copernicus is one example how we can move from a pure download system to a more cloud-based data system where users can also have access on demand. And at the same time also because meteorological and climate data, they can be complex. We often need expert knowledge also to understand many parameters. And the Climate Data Store really works to bridge the gap and to make the data better accessible and also better understandable to users, to the general users. So just a quick overview of the Climate Data Store. The current, there we see we have more than 11,500 users registered, but the latest numbers is now we even have more than 12,000 users registered. So people use it. It's quite a few data from academia or research purposes, but also companies and the general public are interested in the data. Most data downloads come from China and United Kingdom, United States and Germany and France. But probably what is also most interested is the figure on the bottom left, that we have around monthly data. The data that is retrieved monthly is continuously growing, and in January it was around 500 terabyte, which was being made available. The general vision of the Climate Data Store is to make it easier to access the data and also to discover the data, then provide scalable data access because the data volume is growing, and we need the data systems ready for it. Then at the same time, a online capability for users who are interested to process and execute workflows directly within the Climate Data Store. Then also to define and showcase some example workflows to see, and which is also easy to use online for users to use the data and to have examples how the data can be used. And then this comes everything together to enable Yeah, most people identify themselves as data user, around 72%, and the most job titles they indicated were researcher, which is almost 50%, but also data scientists and data analysts. How is the data used at the moment? So we ask what kind of data do you use at the moment, and also what data are you motivated or would you like to use in the future? This is the graphic on the left, and then we ask, okay, is like for the reason, so why? So for all the data you would like to use in the future, what is the reason you don't use it at the moment yet? And so we see on the left, it's quite a lot. So we gave an overview of climate reanalysis data, Earth observation data, environmental forecasts, seasonal forecasts, but also value-added products and general geospatial data. And what we can take from this graphic is that, like, yeah, a lot of already use Earth observation data, and the rest, I would say, they interested actually to use it in the future. But we can see that there's quite an interest in forecast data, so like environmental forecast data. Can I actually also point? But no, it's hard, huh? Ah, yes, yes. So. Yeah, like environmental forecast data and also seasonal forecast data. Not many people use at the moment. Oh, sorry. Yes. No, I would like to point. It was okay. Yeah. So, but there's like a motivation to use the data in the future. And if we ask, like, okay, what is the reason you don't use them yet? So we gave them some options to choose, like, is it time, or I don't know where the data is to find, or it's uncomfortable to download the data. And it's quite scattered. So like, most reasons, or many users, they said, okay, like most reasons, it's quite distributed. We see, like, okay, often it's more time constrained actually to have time to get familiar with the data. Then data handling. So we ask how people access data systems, and so what they use currently, what data systems they're not interested at all in the future, and what data systems they actually would like to use more in the future. And this is the left graphic. And then we also ask about the satisfaction of the data access services. So, like, how satisfied are you with the data access system you use at the moment? And what we find here is, I try to point again. Oh, no, this was wrong. Okay. No, this is okay. Can I also? Here I go back. Okay. Yeah, we see here that so like most people, they download data. There's not a big and of course they said, like, they actually not interested in downloading data in the future. But in the future, like cloud computing infrastructure and also data cube technologies and spatial databases, they quite of interest. Like these new technologies, many users are interested. But surprisingly, even though people are not very motivated to download data, but they still say they actually quite satisfied with the download service they use at the moment. So overall, like on the right graphic, we see there's actually quite a satisfaction in the data access systems they use. Then programming languages, Python is the leader, but then directly followed by R. Also, a lot of people use GDAL and slightly less JavaScript, and also Fortran, which probably is meteorological and climate community. But also, almost 60% said they use desktop-based services, software. And there's, QGIS was mentioned most, followed by ArcGIS, and then even Excel and GraphGIS. Data challenges. It's a bit hard to read. So yeah, we asked different challenges they have, and to ask them how to indicate like from no challenge at all to a big challenge. And yeah, like growing data volume is of course a challenge. Limited processing capacity is quite strong. That data are disseminated in a non-standard way. It's also like 50% said it's a challenge. Too many data platforms on portals. It's also 50% said like, yeah, it's too many. And at the same time, it's also followed by data discovery. So that finding data sets and to see actually what is out there is quite a challenge. Future data services. So there is quite a motivation to migrate to cloud services. So around 67% said, yes, actually I'm motivated to move my processing tasks to the cloud. Then we asked like, okay, if you use the cloud, is it important that it's a publicly funded cloud, if it's a private cloud or commercially cloud? And a lot of people, or not a lot, but most said like more than 30% said, okay, if I use the cloud publicly funded, I would prefer a publicly funded cloud. But then also around 25% they said, actually, I don't mind what kind of cloud I use. How do users want to interact with the cloud? Yeah, they interested in data access, data processing, and data storage most, but and then how they want to interact. Like for example, we asked them if they want to have an opportunity to upload also other data sets in order to combine data in the cloud, or if they need to export the data out of the cloud, if they want to work more in a collaborative way or more privately because they don't want to share. And yeah, a good sign is that many or more people said they would like to work in a collaborative way. They want to share code and workflows. They also want to have an opportunity to upload data to the cloud and also to export the data out of the cloud. Then we ask also for the willingness to pay for cloud services, and if yes, like for what data services they more willing to pay. And like, yeah, around 50% said, yes, we are willing to pay for the cloud, and but it depends on the cost. It depends how much it will cost. And most people are most interested in paying for data processing, followed by data storage, and then to a lesser extent for service support and for data download. And how much they would be willing to pay is like around most people said like around 35%. They said they would prefer a costing model, and then the differences like just some they said they would even be willing to pay more than 100,000 euros, and then but others they said okay, like the limit is 100 euros or 500 euros. Outlook on next steps for this user survey. So this was their preliminary results. What we can conclude for now is that people are motivated to migrate to cloud services. As we all probably know, is that the growing data volume and the limited processing capacity is a challenge at the moment, but also the quantity of data portals and data discovery are major challenges users face. If they are willing to actually migrate to the cloud, but for pricing, they would rather prefer a costing model like on a monthly or annual basis. So there are preliminary results, and the data, like, because this was just a really descriptive overview, we will have more in-depth quantitative statistical analysis on it. We also plan to have to see if we can actually define different data user groups out of the sample. And then we also want to have some follow-up in-depth expert interviews to get some more information on it. And the data survey is still open, so if we have here data users and you would like help us to shape future cloud services, please participate. It's bit.ly and then user survey Big Earth Data. Yeah, then thank you for, for your time.
Okay, thank you, Julia, for that very interesting presentation on the Climate Data Store and also on the user requirements. That's very illuminating as we think about the GEO Knowledge Hub and how we want to move. Okay, our next presentation is going to be given to us by Matthias Mohr from the University of Münster. He's a software engineer working on the Open EO project, which we'll hear about in the next presentation. He's currently leading API development, and through that got into the STAC, Spatial Temporal Asset Catalog, which he is now a core contributor to. And he also has a master's degree in geoinformatics and has worked as a software developer for several years in industry. So he's going to talk to us about STAC.
Yeah, thank you for the introduction, and thank you for the nice outlook that I now can use for my presentation. So I'm talking about or giving you a short introduction to the Spatial Temporal Asset Catalog. I would like to start with why do we start with the STAC specification. And you actually just said that there are too many data portals and it's a challenge to discover the data. So nowadays, gigabytes of data are generated each minute, and every data provider basically has its own data portal. You see some examples up there. That's a lot of potential we have now, and now we need to make use of this data. But how do you find your data today? We already figured out for web pages that a single entry point like Google is much better than many data portals. I think you still remember Yahoo, which is now obsolete. And Google makes sense of the data which is on the web with a single search. And the same we would like to do with STAC. So we have one uniform way of describing spatial temporal data, and having then Google or other search engines to crawl the data and make it available to others, like Google already did it, started it with a Google dataset search, and others will probably continue with that. And for that, STAC aims to make all geospatial assets available to such search engines. And in addition, currently many standards and proprietary solutions are implemented by data providers. They're all like APIs, but they differ in scope and have different capabilities and differ in slightly smaller things. And that's a big barrier for adoption. And that's why STAC came up. So what is STAC? So STAC is a common JSON-based language for geospatial catalogs and assets. And its focus is to make the data available for search and discovery. So it aims to be simple to understand and simple to implement, also for non-geospatial experts. And STAC is an open source project which is licensed under Apache license, so everybody is very welcome to contribute and join the effort and yeah, just define whatever you need in STAC actually. STAC allows to define static catalogs, so you can just put your metadata files to the actual data files and host it somewhere, or you can define an HTTP API, which just you can filter or do whatever we want with in a dynamic way. What is STAC not? STAC is not meant to be a full-fledged metadata standard, such as the ISO 19115 standard, for example. So that lives side by side with STAC. And the actual source of truth for your metadata are still the full standards that you're using, like the ISO standards or whatever you're currently using. STAC is also not intended to cover all kinds of data sets. It's basically limited really to geospatial assets and collections. But of course, it's extensible, so you can add your domains that are in this range of data to be supported by Stack. We're not trying to replace these full-fledged meta standards, as I said, and we actually aim to align with as many of them as we can. For example, for items, we are currently using GeoJSON. Then there's JSON-LD, which we are outputting for Google to be crawled. The API is actually compatible to OGC WFS 3.0. And we also aim to align with the new version of OGC CSW. So when did it start? Stack is actually a pretty new effort. It started in October 2017 with a kickoff meeting where several organizations came together as they saw the demand for that and wanted to contribute to a uniform and approach to that problem. Currently, we are now in April 19. The current version is Stack 0.6.2. Which added additional content such as the SAR extension and the point cloud extension. So at the moment, we're trying to use the small core we have and extend it by several extensions that add domain support, for example, for SAR data. Then we have every now and then Stack sprints that are held usually by Radiant Earth, where interested parties and all contributors are coming together to discuss related issues and the most pressuring ones. Often they are combined with other efforts, like the second sprint was together with WFS3, where we decided to align, and the third sprint was with the analysis-ready data community. And here I would like to invite to the next sprint in June, which is in San Francisco. These are very welcoming in general, and you are welcome to just join if you would like to learn about Stack, for example, and or want to get first experiences. Another interesting thing is that we plan to release a first stable version at the end of the year, so that you have something stable to work with. So who is Stack? Actually, it's led by Chris Holmes and generously sponsored by the Radiant Earth Foundation. And the images here you see are basically the main contributors to the specification at the moment. Now I'm coming to the actual specification. The specification are loosely coupled small pieces. So we have basically 4 or 5 parts. There is the collection specification, the catalog specification, the item specification, the API specification, and the extensions that add more functionality to all these 4 other specifications. And I'm now going through all of them. And basically, a catalog in Stack is basically a very simple piece of JSON file that is only there for grouping other collections or items into subgroups. It just consists of an ID, a title, a description, and links to sub-items. And the collection then is an extension to the catalog, which actually adds collection-level metadata. Things such as extents or the licensing information, provider information. You can see an example here in the image. And all of that can be also used standalone. You don't need to actually export your assets or make them available in OpenEO and Google Earth Engine, which were the main drivers for the collections. We're just using the collections to show which data is available, and we don't offer it for download at the moment. The collection extension works very well with the Commons extension, for example, where you can move all your duplicate data from the items to the catalog, to the collection, so that it doesn't replicate all the data in single files. Then we have the item specification, which is basically a GeoJSON feature. which holds all the metadata information from your domain extension and some basic information like the date and bounding box is, of course, already in the GeoJSON file and the geometry. It links to the downloadable assets. That's basically an asset is a file a user would like to download. And items really shine with cloud-optimized geotiffs, which you can see in this example here. It's basically just a static file written in stack that links to a geotiff file here. And this OpenLayers map, I think here, just loads whatever data is required from the cloud-optimized geotiff when you request it. So it's basically optimized for HTTP GET range requests, so you only need to transfer whatever you need for your for displaying on the map. Then we have the API specification, which is fully aligned with the WFS3 specification, and we added some endpoints on top, like search functionality, which is not yet in WFS3. But once we have search and filter functionality in WFS3, we are probably aligning with them again. It's defined as an Open API 3 document, so should be very easy to implement. And we also have a plan to align with the CSW 4 once it's available, but that's not yet a thing, and we're waiting for that to happen. Then we have the extensions, which are basically the most important thing in the stack specification, as it allows you to define the domain-specific information. So we have, most importantly, the EO and SAR extension, I think. EO in this case here means electro-optical, not Earth observation. Then the SAR extension, and recently also introduced the point cloud extension, which is very nearly coupled to PDAL. That's basically content extensions where you add extra fields that describe a specific domain. And we are looking forward to get more of these extensions in, for example, for meteorological data or other domain fields that are still missing. Then we added a data cube extension, the comments extension I spoke about, and have more smaller things like a scientific extension to add DOIs to the files and stuff like that. Then the API was extended by a transaction API, which adds create, read, update, and delete behavior to the API, which the basic API is just reading, but then you can also like delete parts of the catalog or something like that. New extensions can easily be proposed as PRs. We're always happy to introduce more and discuss things with you. Then a short word on the Stack ecosystem. We have several tools already implemented to display stack catalogs, for example. There is Stack Browser, which renders stack catalogs nicely in the browser, so it can be crawled by Google also or other search engines. It can be persons to explore the data. And it also includes a JSON LD encoding based on schema.org, so it's easily findable in Google Dataset Search. Then we have Stack Validator, that is an online and also offline tool for the command line, where you can validate your stack catalogs. There is Stack Crawler, which is a serverless crawler based on Amazon Lambda and SQS. And the last thing developed by Development Seed is setutils, which are mostly Python libraries to work with Stack. One is for searching APIs, one is to create actually stack catalogs, and there are some other tools that help with that. So for such a small time we had, there's quite a big ecosystem currently available, but it's all work in progress, and you're very welcome to contribute to that as well. And the main thing you see here is basically, I think, that Stack is implementation driven. So we're not thinking in advance, but we all back our theory or our experiences with implementations and check regularly whether everything works as expected. And we're looking for feedback all the time so that we know whether we are heading to the right direction or not. And that's it basically from me. I would like to close with a effort, with a call for you to join the effort if you are interested. Feel encouraged to get in contact. We're a very welcoming community, and we are always happy to see new people bring in new thoughts and proposals. Thank you very much.
Okay, thank you, Matthias. I learned a new word, crawlability. I'll have to think of a way to use that before the end of the day. Next up, we have Edzer Pebesma, University of Münster, who is a professor in geoinformatics. He's also the technical coordinator of the Open EO Horizon 2020 project, which he's going to speak to us about. He is a member of the R Foundation and is editor of the Journal for Statistical Software. And in his spare time, he enjoys messing with analog photography and playing music. So we need to talk afterwards.
Thank you, Doc. Right, so this talk is about challenges in harmonization in cloud computing for Earth observation. I apologize for my slides. I'm not a PowerPoint user, and I made an effort, but I doubt whether that was a good idea. So we hear a lot about cloud computing and Earth observation, and cloud processing platforms sort of popping up like mushrooms. There are so many, and they're all doing essentially the same thing, but in slightly different ways. And so we have a problem, a challenge there that I'm going to talk about. So interoperability, just to refresh your minds, this is not a definition that I came up with, but which I will read aloud anyway. Interoperability is a characteristic of a product or system whose interfaces are completely understood to work with other products or systems, present or future, in either implementation or access, without any restrictions, with some emphasis on without any restrictions. So you can go with interoperability, do that, and take basically different approaches to achieve that. You can achieve that, try to achieve that by adopting formal standards, for instance, ISO or the OGC standards. You can also do that by adopting de facto standards, like existing open source software. So a lot of people think standards directly think of formal standards, right? But so software standards, de facto standards, is basically the software that everyone uses, like Python and R, where there is not a formal body or so saying that sort of says this is the standard, but there is essentially a source code base that everyone agrees about and that everyone understands, and so we can expect what it does. And the advantage of the second over the first, I would say, is that you can actually use it. Yes, and with formal standards, basically they're on paper, so using that might not be sort of trivial, depending on sort of what is offered in terms of implementations. And another approach is, if there is not a solution to your problem, is by developing new versions of software, and possibly that can also lead to new versions of formal standards. Formal standards, here are some examples that are relevant. I think that are relevant. Maybe I forgot some. For Earth observation processing in the cloud, there is the web processing service, which I have, a long history with. There is a lot of activity in Münster actually going on the web processing service. It's a layer of complexity. It's not dedicated to any particular process, and so the question is, like, if you want to do things that Earth observation researchers want to do, what is actually the benefit of using WPS? There's nothing against it, except maybe complexity. Web coverage service is highly interested, but it's for downloading, not for cloud processing. So that's another thing. There's the web coverage processing service, which is complex, yet it's too simple. It doesn't have a lot of the functionality that Earth observation research needs. It's in principle a very good idea, but there are some restrictions. Basically, there's a vendor lock-in, unless you want to sort of build in.
So if you look at these little yellow boxes, this is what our neural network identified as having a high probability of a high voltage grid tower. So this machine learning model output was paired then back with the human mappers to basically create a complete map of the high voltage grid in 3 developing countries. And what's also cool about this project is this high voltage grid data that we produced was contributed back to OpenStreetMap. So now this data on the high voltage grid in these countries is openly available. So what have we learned from this project? From these projects is that insight is derived from partnering human expertise with machine learning. We've also learned that we really need better geodiverse training data. So a high voltage grid model in Tanzania may not work elsewhere. And in response to these learnings, we're moving forward in not just delivering solutions for scientists, but also getting data into the pockets of decision makers and citizen science. So we don't want these just to be web applications. We want them to be end user applications that people can use on their mobile phones. So my boss, Ian, LibreLive, has demonstrated LibreLive, I believe, at GEO events before. So this is a mobile application that basically does on-demand, real-time, or I should say more like on-demand road mapping. So when a user brings up this application, they can say a location, and then as they pan around the map, this is on-the-fly machine learning predictions of roads. So one of the cool things about talking on the second day is that I get to relate this back to some of the existing projects. So there's a lot of places of overlap. I'm just numbering a couple of them. I'm enumerating a couple of them here. So the Grid 3 project and the Sendai framework for disaster relief. So the next challenge that we hear from scientists is I just want to collaborate with my remote colleagues. So a project that I've been working on for the past year is the Multi-Mission Algorithm and Analysis Platform, or MAP. And MAP is basically a collaboration between ESA and NASA. So it's going to be supporting the biomass community in creating global biomass and uncertainty maps. So we are building a science-focused virtual environment for scientists to share, process, and analyze data from ESA and NASA field, airborne, and satellite missions. And this is really cool because it's a new platform basically combining, which enables access to both ESA, critical NASA and ESA missions, including Biomass JEDI and NISAR. However, this platform will include probably about over 80 data sets, ancillary data sets, in addition to these core data sets. So I have now a couple of screenshots showing what this platform looks like. It's still in a prototype phase, but so this animation is basically showing how we're using NASA's Earth Data Search client to support the user, basically having a really good experience where they're able to go into Earth Data Search that they need by drawing an area of interest, and then copying those search results directly into their development environment, and then use those results in analysis. This animation is our interface for basically a user who might want to interact with the dynamic tiles of LiDAR data. And then finally, this animation is basically showing the workflow of a user that might want to run an algorithm. So another thing that's come up a couple times is the ability for these open science platforms to enable scientists and researchers and developers to share algorithms that they're working on. So this is something that we're developing as part of the map, basically where the user is able to go search for an algorithm. Once they've discovered the algorithm that they want to use, they're able to actually submit a request to run that algorithm against the data that they're using in their development environment. So what we've learned from working on this project, there's more complexity in policy than implementation. So I think this Fish said yesterday, which is basically that there's more, the problem is in coordination, not in will. So we definitely want to build this thing. We know what we want to build. However, we still have to answer questions like, how do we trust, share, and publish user data? How do we share compute resources while restricting costs, and other similar questions? Another thing that we are still learning, or we haven't quite learned yet, I think, that we really are building this platform for a couple of the scientists that we're working with directly. However, there's no one-size-fits-all platform for scientists. One thing that we've heard is like some scientists really aren't ready to jump on board to a development environment or a Python environment. They need an R environment, or they need a GUI. They need something else that we're not currently building for them. So moving forward, we do want to, work on, standards and things that might work across different applications. So now we are developing metadata models and standards for algorithms, or somebody mentioned yesterday they're called algorithm theoretical basis documents. Also developing metadata models and standards for things like software, web processing services, data collections, web mapping. So this is to echo the idea that applications can differ, but backends can be reused. So one example of this that we're currently working on is basically NASA and ESA both have imagery. We want to be able to visualize each other's imagery on different applications. So this is where we're working on the OGC web mapping tile service standard and developing that within our internal APIs. So this is some related geodata tech projects. Geo Knowledge Hub is also working on this problem of sharing the reproducibility of science. What does that mean? Other, domain-related projects measuring deforestation with LiDAR, biomass and uncertainty maps, and basically the complexity also finally in something we just heard this morning about heterogeneous and complexity of in situ data. We're also addressing that with the biomass in situ data that we are going to be handling. So finally, I just want all the data I need to be in one place. So some of you might be familiar with NASA's distributed active archive centers. This is what NASA's been using for many years to basically ingest and process and archive its data. However, these on-premise data centers are really not sustainable for processing and archiving and basically distributing all of this data. So some of you might be from, as I mentioned earlier, there's the upcoming NISAR mission. Basically, NASA is going to be experiencing an over 10-fold increase in the volume of data that's going to be collecting per year, going from 4 petabytes in 2017 to over 40 petabytes, or approximately 40 petabytes a year in 2022 after the NISAR mission launches. So this is really, sort of not sustainable if they want to be, publishing all of this data for people to use. So the ESDIS, Earth Observation Division within NASA, is moving to a new cloud paradigm, and the software that Development Seed is working on in coordination with NASA and other partners is Cumulus. So Cumulus is basically the software that is going to be that the data centers are going to be adopting to move their science processes and data archival processes to the AWS cloud. So what we've learned, getting DACs to use one unified approach is not easy, but the investment may be worth it in the long run. Scientists, decision makers, and developers all need data in different formats and access patterns. So now we're working with scientists and NASA to make more analysis-ready data formats publicly available. So problems and solutions. You guys have seen a slide like this sort of yesterday, so I'm going to skip over this part. I really like Robert Chen's version of this slide, so I decided to directly copy it, but give him appropriate accreditation. And as data providers, we're still learning. We're experiencing growing pains. If you guys might recall, it used to be hard to build a website. Now it's pretty easy. There's still lots of ways to do it, but some cost money and don't, but they're all pretty easy to do. Most of the current solutions are new and have limited adoption, so there's really an opportunity for us to all work together on these existing tools where it's appropriate to enable rapid development of new applications for open science and tools for decision makers. And this is a very rough attempt at demonstrating the landscape of geospatial technologies landscape. So this is just something I produced in the last couple of days. I'm sure it's wildly incomplete, but basically it just shows how the system is already very vast, and it also feeds my need to sort of compartmentalize things so that I can feel like I'm slightly in control when I'm not. Finally, in summary, moving to the cloud and ARDs, and suddenly I don't need my own copy of the Landsat archive and my own supercomputing cluster to do research on decades of Landsat data. I can just grab the pixels I need. I can drop imagery directly into mobile applications as it comes off the satellite. I can create image chips for my AI applications without an army of grad students. And Finally, I can build collaborative science tools that allow scientists to work together on huge data sets,
is that we need to partner human expertise with machine learning. So humans won't, I think for the time being, humans will not be replaced by machines. And there's definitely a role for us to play, especially in mapping, doing. I participated in a
I think
simple to adopt. When I was looking into Stack the first time, it was just like a GitHub repository with some pages which I could easily read through and implement in like a couple of hours. When I tried to look into the ISO standard, for example, I had to first buy it, which I didn't do, and then you will basically get hundreds of pages. The same as for several OGC standards. And also
advantage.
So the question I raised is, when I do, as a scientist, when I do a computation somewhere, how am I going to check that the outcome that I get is the right one? And if you sort of accept vendor lock-in, then you can't do that. Yeah. So it's okay if you trust everything, if you are convinced that everything works, and if you are an engineer, you want to get something done, some kind of prediction you want to get out. So then it's no problem. But if you're kind of trying to do science, you need to be able to sort of find out what the details are of the software, and you need to be able to validate, to do comparisons, and to check reproducibility.
I think when the login becomes a problem if you don't have any control as a user on top of it. So my worry would be, say, if universities would be forced to go on existing commercial cloud services, that initially it may be cheaper, but in the long run it may become significantly more expensive. And then you have a problem if you cannot move away any longer because you have lost all your expertise.
I was actually going to go back to the user feedback question, because what I realized is that we're more focused on being user driven. So with just thinking of the projects that I mentioned earlier with the map platform, we're actually, all of the requirements that have been defined for us are actually by science users. So I think this is one thing that Development Seed and our partners all value, is basically building applications that are built based on requirements that have been written by users. So it's really user-driven first. And then, like I said, of course, we would continue to collaborate with those users, both as development continues and as well as things become productionized to incorporate user feedback through things like forums and surveys.
Maybe still add another thing. In the long run, having to just learn API or standard like OpenEO, for example, once for your developers, is much more cost effective if they do it just once and don't need to look into all different APIs or data providers. And so they don't need to relearn everything, and you can easily switch between platforms without spending
where the climate data store is heading to offer the workflows, the
Convergence between stack and WFS3. Can we expect that conversion to happen? Or will they evolve separately?
So we're trying to align as much as possible, and we're now seeing that WFS3, the second draft, is coming forward, and we strongly want to align stack with WFS3 again. And in the long run, we also want to push OGC CSW4, that is planned to take over our experiences and combine them with their experiences from CSW3. That should work, I think. Other things are more open, like there are other standards like DCAT, JSON LD, GeoJSON LD, and so on, and ISO standards. And of course, we can't align with all because they are diverse and different. But we're trying to align with them, which we think, or the community thinks, are the most future-proof.
Okay, another question from the floor. Okay, yes, please.
It's mostly a comment. It seems to be there's a very little amount of time spent in the distinction of Google Earth Engine service as Amazon Web Service. Amazon Service is loosely coupled components that allow you to do a lot of things. Google Earth Engine is a software stacked on top of their cloud platform that allows you to do a lot of other things. Earth processing, Earth system processing, whatever you have you. That was one comment. The other thing I wanted to clarify was, I lost it. Oh yes, the adoption of Stack versus WFS3. It's the community is so engaged that eventually the community will decide which file format, which service format what they want to use. So I think we should trust the community, and eventually either Stack or WFS, or they'll merge, they'll fork, it'll work out itself. That's how I've been doing this for a while, so that's how I've seen. There was a long time that GeoTIFF was not adopted, and HDF4 and HDF5 and HDF EOS and then NetCDF came along, but then the community want to work with GeoTIFF. We want to see what we're working with, and the scientific community said, okay, sure. So.
Okay, I'll go back to just a couple more questions here, and then we'll a conclusion. Let's see, there's a question here. How do we get more developers into the Earth observation domain? Sir?
By educating them how to develop. So, no, I'm kidding, but we run a program for 20 years now in geoinformatics, which is kind of 50% computer science and 50% geosciences, and that really works. There's a very strong demand for people who understand both. And experience as geoscientists, it's difficult to communicate with computer scientists and solve problems together. So it's really by educating people, geoscientists, Earth observation, researchers, that coding is part of the daily job. It's data science.
And me as a software developer, it's basically you need to give them things that they can understand. They don't want to read 200 pages of documentation. They want like an example and then 2-3 pages of getting started, and then they can start with implementing, and during that time they will figure out how things happen and how to implement. And you need to speak their language, give them tools like open API specifications so that they can easily implement with things they know how the things they need to implement actually to make Earth observation for a better cause.
Yeah, I think from my experience at the university, I see it's a very attractive field. So we see that students are coming, and we have really good students who can now combine both the expertise on the IT side and on the remote sensing side. And once they go into practice, they bring this new knowledge into the daily life. Of course, there's always, need this next generation to have this paradigm change implemented. I think it's going very fine. Just one comment I would like to make on this machine learning thing on artificial intelligence, because this is kind of often sold as the one thing that is missing to make things happen. As a physicist and geodesist who works with data, knowledge on the data itself is as important as all these other machine learning tools. Yeah? If you just do machine learning, you always find that you need to drill back into the data and get an understanding of the processes, and only then you can use machine learning correctly.
Okay, Edzer, you have been singled out for a couple of questions here. Let's see. They're kind of along the same line. Can we try OpenEO APIs in practice somewhere?
Excuse me?
And how far away are we from being able to use OpenEO operationally?
Second question, a couple of months. First question, yes, you can try things out. There is a nice interface, there is a website, openeo.org, and a nice OpenEO hub, hub.openeo.org, where you can try out things, but it is all kind of, running locally, so it's not massively scaling, and it's only, of course, things where you don't need user credentials and things like that. Yeah, so we're starting to crawl, but anything that we get running is essentially running for everyone. And we are happy to share also user credentials with anyone who wants to try out something. We got user credentials from Earth Engine to sort of do scalable computing there without doing the complex authentication and so on.
I see a burning question over there.
Thank you. See, about the previous question, like you were mentioning about how to make more students into the same field. I'm a master's student in aerospace engineering. Let me tell you fair and square. People in the aerospace industry doesn't have a clue to a greater extent. Only very few selected universities are promoting geospatial data or remote sensing or earth observation, whatever it is. In my university, for example, nobody understands like the spectral bands, when they are divided into multiple different layers, we can extract different data from them, which can be utilized for different other purposes. I think it should be like that. Like people should be more told about what are the benefits. Like forget the Mars mission. We have an Earth to save, and we have the possibility to save. And this sector is one of the most exciting as well as promising thing that we can do towards the same, like climate change, everything. But nobody is being teaching about this. Nobody is being informed about this. That's one of my concerns. Like if you want to get students, first and foremost is the aerospace students. You need to inspire them. You need to get the information to them. Like these are the things that we can do about it. So that's just my contribution. I just wanted to say. Sorry.
Okay, thanks. Any response? Yeah, Amy?
So one thing that the University of Washington is doing, I don't know if maybe you guys are familiar with this, but they're hosting these hack weeks. So they're having a ISAT hack week in June and a GEO hack week in September. I think that this could be a really great way to get more students and more developers involved by having some sort of hackathon aligned with a GEO conference. That would also potentially solve this problem of getting developers and students with domain experts. There's a lot of domain expertise in this room. We could have projects where there's actually partnering people who have domain expertise in some of these science domains that we've been talking about these past 2 days, partnering with the developers and actually giving them information about the domain that they are an expert in while they contribute to some project. I would be very interested to see that happen. Yeah, if there's an opportunity to do that.
Yeah, I would fully agree. Also, like, to bring communities together. But what I realized some months ago when I was talking to students is that, like, what we discuss here, like throughout these 3 days now, we have to bring the knowledge and also the current status quo to the universities at the moment to prepare people for the future to work in this sector, because universities often teach still like that data has to be downloaded and then they do their local analysis with ArcGIS or QGIS, but not a lot about Google Earth Engine or Jupyter notebooks or the cloud, how to use it. So yeah, this is, we really have to make a stronger link on what is actually happening and bring this back to university.
Okay, one last question here. This is something I'll just kind of throw out to anybody who wants to take it here. But, and I think, Wolfgang, you've already responded to a certain extent to this question, but more broadly, has anyone here among us done a comparison of the different cloud services in terms of costs, capabilities, limitations, and what, you know, if you're sitting here as someone who's leading an initiative in the GEO work program, for example, and you're thinking about going to cloud services, where do you go? How do you figure this out?
I would say it's extremely difficult, and it depends on the functions that you want to implement, what the goals that you're achieving it. So again, like from our perspective, when we do this very large scale data processing, high resolution, global scale, I don't think that you can compete like with supercomputing facilities for scientists, because they can give you good conditions as a scientist. But if you, for example, again want to kind of bring the data to the user and high performant access on different continents, and the data sets are smaller, then you would go to a cloud. So it really depends on what exactly you want to do. And if you want to do a real-time processing that is reliable and etc., again, just buy some dedicated machines that are just doing the one purpose. So there's not the one solution that does it all.
And I think with OpenGeo, now that we are defining a specification, processes, and compare these things, to define this API, we need to know what the backends offer and what they can't do. We need to specify processes. Therefore, we need to know what processes are available on the backends. Actually, we need to define an API, so we need to know which functionality actually they have in regards, for example, how they handle user-contributed files and stuff like that. We need to know how they export or show or let the users know which collections or data sets they have. And we're actually also at the moment comparing with the master thesis with how the results from backends actually compare. So we're running the same algorithms on the backends and comparing the results from that are returned from our OpenEO backends. And that's currently in the progress. So that's, I think, mostly the closest we can get at the moment.
Well, so Cumulus is this pipeline that we've created, or a software for configuring data pipelines for NASA's archives. And that was actually built on, it was built basically cloud native to AWS because it was built, is designed and built before Google and Azure are as mature as they are now. However, we've been working on a sort of feasibility study of making Cumulus cloud agnostic, or at least creating a version of Cumulus in those other cloud environments. It's ongoing, but preliminary results are largely that AWS as a cloud provider is much more mature still than Google Cloud Platform and Azure. So from a development standpoint, the resources it would require just to have developers build the same type of infrastructure we're able to get out of the box with AWS would take many months and might not actually be worth the cost of transitioning over if we're going to plan to rely on AWS anyways. That being said, there's a big asterisk there that we do think it would be very valuable for Cumulus to be cloud agnostic if we have time to implement such a thing.
Okay, and I think this is also something that the GEO Knowledge Hub, again, we would like to address is, as you've heard, we'll be looking at providing in one place documents, a document of documents with methods, algorithms, and any cloud computing services or resources that were used. So that might give an indication of the type of applicability of that particular cloud service for that